Hi, in this video we are going to explore the ARM processor. In that we are going to discuss about the ARM processor memory organization. Let's recall the last class topic, that is Introduction to ARM processor. In that we covered the architecture of ARM processor and a development tools that includes the software and hardware tools for ARM development, interrupt handling mechanism, instruction set, and power efficiency, and we see about the memory management techniques for organizing and allocating the memory. Let's see about the today's topics for discussion, as we covered 4 key areas, that is ARM memory architecture overview, understanding memory maps, Raspberry Pi GPIO memory mapped input output, and we covered the endians of byte ordering in memory management system. And now see about the ARM memory organization, unlocking system performance. Why this is so important? A deep understanding of ARM memory is critical because it directly impacts system performance and reliability and our ability to debug effectively. This knowledge is essential for both bare metal and the OS development. Next we see about the ARM memory architecture overview. In that, let's start with the architecture overview. ARM uses a RISC design. We know that the reduced instruction set computer architecture. It is optimized for embedded systems. It supports both hardware and von Neumann architectures, so it offering the flexibility. Furthermore, advanced Cortex A processor include an MMU for virtual memory management and cache hierarchy for memory access. And next we see about the empathize part of the understanding memory maps. In memory maps, it includes the ARM core, memory protection unit, and SRAM peripheral input output, and serial wire power, and ETM, WIZ, and NVIZ, etc. The memory map, think of this as a logical layout of your system address space. It defines where RAM, ROM, peripherals are alive. For instance, on a Cortex M4, flash might start at 0x0 and the SRAM at 0x260. Peripherals get their own dedicated address, allowing software to control hardware directly through simple memory read and write. Next we see about the demo part of the Raspberry Pi GPIO memory mapped input output. Let's see this in action with the Raspberry Pi. Its GPIO is controlled via memory mapped input output. The base address has changed between modes, that is 0x3F240s for older pins and 0xFE240s for the pin 4. By writing to register at offsets from this base, like the function select register, we can directly set a pin as input output, giving a fine-grained hardware control. Next, see about the defining stage, that is the endians for byte ordering in memory. We have defined the byte order, that is the endians defines the byte order for multiple byte data. This applies to 32-bit integer, for example. Little endian means it covers the least significant byte, that is LSB, that is stored at the lowest multiple order. Big endian is the most significant byte, that is MSB, is stored at the lowest multiple order byte. But the ARM processor supports the both big endian and little endian, but the default endian is a little endian architecture. Now see the endians example, that is 0x12345678, the data value. The little endian is 0x78, that is stored in the memory 0x1000, At the same time, the 1000 address, the big endian is 0x12. The 1001 address, the LSB is 56 and the big endian is the 34. Finally, the little endian ends with 0x12, that is the MSB value, and the big endian ends with LSB value, that is 0x78. And this is why understanding endians is vital for data communication and interpretation. Next, we see about the memory alignment for optimizing access. Moving on to memory alignment for best performance, data should be stored at addresses that are multiples of their size. A 4-byte integer should be on a 4-byte boundary like 0x1000 or 0x1004. This allows the processor to access data efficiently in a single cycle. Misalignment can cause huge performance penalties or even hardware faults. Now let's move on to the case study, a simple case study of misaligned memory access crash. Consider this case study casting a character pointer to an integer pointer on an odd address. In older home chips, this caused an immediate crash, a data abort. Even on modern cores that handle it, the performance cost is severe and the debugging as the resulting data corruption can be nightmare. Next, we say about the ARM assembly load store alignment. This is an ideate stage of the design thinking. The LDR is nothing but the load instruction and STR is the store instruction that are used to move data between registers and memory. These instructions are most efficient with properly aligned addresses when debugging tools like GDB are essential. In C, we can use attributes like aligned and packed to manage alignment explicitly. Now let's move on to the mind map part of the this content. That is, the ARM processor memory organization includes the importance and focus areas of memory management, architecture overview, and it gives the memory maps with endians byte ordering. It includes the little endian and big endian, and memory alignment which includes the assembly instructions like load and store. And now let's move on to the conclusion part of the ARM memory fundamentals. For understanding ARM memory fundamentals is the key for robust embedded systems. Memory maps access blueprint and endians gives the correct data interpretation and across the embedded systems. The proper alignment is vital for performance and stability. Now let's move on to the assessment section, that is, if the 32-bit hexadecimal value 0x12345678 is stored in memory starting address 0x1000 using a big endian format, what byte value will be found at address 0x1001? We know that in 1000 address the big endian is stored in 12 and the little endian are stored in 78. If the next address is 1001, the big endian is stored in 34 and the LSB, that is a little endian, are stored in 56. So the answer is 0x34. These are all the references. Thank you.